is chapter 8, the normal distribution. And it's going to be on finding z-scores, which we already know about. And then we're going to use standard normal distributions and normal distributions, but we're going to use SALT because we're going to do it a little bit more sophisticated way of doing it. The only kind of normal distributions that we used to do were the guys that looked like this. Can you remember the normal distribution? And in the middle, it was 100 and then went up 110, 120, 130. You remember the guy that did that? And we could do like, well, that middle chunk, for instance, was 68%. Remember doing that? Well, that's fine. It does what it does, but wouldn't it be nicer if there was a way where we could tell what percentage of people got a score bigger than 108, less than 92, or between 45.1 and 67.9, right? Much more detailed results. Now, you can't do them using the technique that we used last time, but SALT has a program, and SALT's just an example of statistics program that will allow us to do that. So we're going to be using it in sections 2 and 3 in particular. I've even written down what question numbers use which. And then we finish with some applications where we get to use it. So remind you what a z-score is. It's sometimes called a standardized z-score. So you have a mean, mu equals a mean. And we have a standard deviation, and sigma is a standard deviation. And you might say, I don't remember those guys. I remember the mean being called x bar, and I remember the standard deviation being called s. Agreed? Now, this fella here, that is a Greek letter, and you pronounce it mu. And this funny little here is another Greek letter, and it's called sigma, because we are going to be looking at the mean and standard deviation of populations. So when you talk about the mean and standard deviation of a population, you'll call the mean mu, and you'll call the standard deviation sigma. And these guys here, well, that's the names that you use when your information typically is a sample. So if I collected 400 people and I found out their average age and the standard deviation, I would call the sample mean x bar and the sample standard deviation s. On the other hand, if I knew everything about a population, because I did a census perhaps, I would say that the mean of the population is mu and that the standard deviation is sigma. Are we okay with the new labels, just because when it's populations, you call them one thing, and when it's samples that your data is coming from, you choose another? So how do you get z-scores then? Well, the generic version of a z-score is the data, take away the mean, divided by the standard deviation, right? Well, it's still going to be the data, and it's still going to be the mean, but we'll call it mu, and it's going to be divided by the standard deviation sigma. And we don't even write the word data, we very often call it x. So if you want to find the z-score, data take away mean divided by standard deviation. I'm just writing it with the short symbols, right? The data is called x, sometimes xi. Take away the mean, take away mu, divided by the standard deviation sigma. So let's suppose that we know that the mean of a population is 35 and that the standard deviation is 6. And you want to get a z-score for someone whose age is 42. Then the z-score will be 42, take away 35, and then you divide it by 6. Get my calculator out here. Take this guy and you good idea to put a little bracket around it. So if you go 42, take away 35, close the brackets and divide by 6, the answer, at least to 2 decimal places, is that. Now, I'll put a little bracket in my notes there. You might think, well, what's the problem? Watch what happens if I don't do brackets. 42, take away 35, divided by 6. I mean, that kind of looks right, doesn't it?
That's not going to work.
It's not going to work. So
it's going to divide first because order of operations, and then it's going to subtract.
Yeah. So that's why it screwed it up. It's a little mistake, but it's easy to do. Think about Z-scores in general. If you take normal data, right, usual data, that's probably a better word, typical data, do you know that almost all Z-scores are between -3 and 3, aren't they? You don't normally get Z-scores even in the teens, far less in the 30s. So if you get a Z-score and it's 36 or 14, you've probably forgotten to do the little bracket thing. That's the most likely mistake that's going to happen. Oh, what do we call someone whose Z-score is bigger than 3 or less than -3? You remember what we called people where that was true?
Outlier?
Yeah. Isn't that just the outlier test? Is the Z-score bigger than 3? Is the Z-score less than -3? So we are familiar with the Z-score, so I don't think that in itself is going to cause too many problems. Agreed? Shall I do just one more for fun and giggles, just to see? Okay. Suppose then I tell you that the mean, which is mu, is 14. That the standard deviation, sigma, is 5, and that x is -10. So deliberately choosing a negative number just to make things awkward. So these could be temperatures, so it is possible to get a negative number. So what's it going to be? The data, take away the mean, divided by the standard deviation. Then on my calculator, -10, subtract 14, close the downs, and then divide by 5. And the answer I get is -4.8. So if this was temperatures, and this was a place that during the winter, the average was 14 degrees Fahrenheit, and that the standard deviation was 5, that a temperature of -10 degrees Fahrenheit would be considered extremely cold, right? It would be an outlier for that place. Anything that's beyond the -3 mark. Are we good? Right. So those questions, whoops, are the first 2 questions in your homework from normal distribution. So let's now move on to the standard normal distribution. The standard normal distribution is essentially, it's the distribution of Z-scores. So if you had a population and you were measuring something, their age, their height, their weight, their IQ, whatever it is, how much money they owed, and you took that entire population and you turned everybody's score into its Z-score, you would get the standard normal distribution. It has that bell-shaped curve, which we all are familiar with. For Z-scores, what Z-score do you get right in the middle where the hill is? What number is that Z-score?
0.
0. So that means for a standard normal distribution, isn't the mean 0? Now, when you do Z-scores, don't you typically go 3 standard deviations? In the Z-score world, 1, 2, 3 and negative 1, 2, 3, in that case, isn't the standard deviation 1? And can you see where the outliers live? There's not many of them, right? They're away at the extreme ends. And that is what a standard normal distribution looked like. Now, in the olden days, not that long ago, I might ask you, for what percentage of people, or z-scores in this case, are between -1 and 1? And wouldn't that be 68%? Can you remember the 68, 95, 99.7 rule, right? Now, it did its job, but it is kind of, there's not a lot of wiggle room. So we would like, and I'm going to show you how to do this, we would like to find things a little bit more detailed than that. So here's my guy again. You know, 0. I'm just randomly picking a number, 1.24. I'd like to know what percentage of z-scores are bigger than 1.24. And that's going to be written down as, what's the probability that you pick someone and their z-score is greater than or equal to 1.24. So we're going to be using these symbols here, right, as a question. So you won't get a question with a picture. What they'll do is they'll write this down, but that's what it looks like visually. What would z less than or equal to -2.03 look like? Well, if I go over here, can you pretend that that's where 2.03 is? And less than would be that little chunk there. And that's how they would write it. What percentage of z-scores are less than -2.03? And we're going to find out what that number is eventually. And I hope I've got enough room for the last one. Suppose I'm interested in z-scores from -1.1 to 0.3. So it would be this chunk in the middle. So what percentage of z-scores are between those two? And that is probably the one that looks the weirdest. Are you comfortable with greater than, less than, and between? Greater than looks like this, less than looks like this, and between looks like this. Hopefully somewhere in your math life, if you've seen these between things, I call them sandwiches, right? So that's a sandwich. So really what we need then is, how do we get to find these mysterious probabilities in the Z distribution? And that's where SALT comes in. So basically, we are not going to do any of the hard lifting. We are just going to let SALT do it for us. Okay. Are you looking, I hope, at the homework thing with a SALT button on it? Question 1, is that what you're saying? Okay, good. There's the z-score stuff that we've already covered. Right, so I would like to find the probability that z is less than 1.96. I wish they'd just written separate questions. This one here is a z-score less than 1.96, less than this number, less than that number, less than that number. So let's look at how to get less thans, greater thans, and more thans. I'm just going to hit this button. Boom. And I'm going to move this guy here. Can you see SALT now on your screen? Right, this guy here's, yeah, just about doable. Can you see it's a normal distribution, which it should be, so you shouldn't need to change that. Isn't the mean for the z-score 0 and their standard deviation 1, so I won't change that. And I want to do a less than, right? When you want less than, you pick this thing here called less tail. And I'd like to know less than -2.03 was the one I've got, so I'm going to use that one again. So I'm going to go negative 2.03. Now, when I click off that, boom, there we go. Can you see the answer is here? Right now, it's a decimal, but I'll convert that to percentages in a few moments. So there's a little picture. Can you see it here? I bet you that's where negative 2.03 is, into the left. And the answer is 0.02118. So I'm going to write that down, I guess, over here because I don't have room. I'm going to just call that 2.1% to a whole number. Now, a couple of cool things you can do with this. See that little guy there? Oops. Click on it. See that little guy there? Right over the number. Suppose I would like to do a z-score bigger than something. Then I'll do a right tail. And I would like to know bigger than 1.24. So I go up here and I go 1.24. See a little picture of it? Can you see the, better not click on it again, but can you see that's exactly where 1.24 is? And what's the chance? How much of the z-scores are bigger than that? And the answer is about 10.7%. I think intuitively, it's quite an easy way to figure out how to do these, isn't it? It's very visual. You got a little picture to help you make sure you're in the right place, and you just put in the numbers. So the last one I had was between negative 1.1 and positive 0.3. And it shouldn't be a surprise, oops, that I use between. And when you get between, this thing here changes a little bit. So on one side, I have negative 1.1. And on the other side, I went up to 0.3 in the question I just did. And the answer is about 48.2%. Do you feel comfortable that you should be able to use this to answer questions like bigger than this, Z bigger than a number, Z less than a number, or a Z between numbers? Do they seem intuitively pretty straightforward? Any questions about that, or can we move on? Okay, from what I can see, they look pretty comfortable, so I'm happy. Let's do the old, there we go. So that answer, remember I've just wrote it down, that was 10.7%, this was 2.1%, and this is 48.2. Watch out for WebAssign. Because it might want the answer as a decimal, it might want the answer as a percent. I mean, whatever it asks for, give it, right? And if they want it to 3 decimal places or 2, make sure you do that. That's just a little nitpicky things, you know, WebAssign wants what it wants, right? So if it says I want it to 3 decimal places and it has to be a decimal, then make sure that's what you do. So far, so good. Right. So let's move on to the next situation, which isn't that different, really. We're just going to do the normal distribution. So when you talk about a normal distribution, what you're basically meaning is everybody else. The standard normal distribution has a mean of 0, a standard deviation of 1, right? That's basically the z-score, guys. A normal distribution is everything else. So let's take an example. The mean of IQs is 100. the standard deviation is 10. If I wanted to draw a kind of generic picture of what that would look like, it would be something similar to what you've done in the past. Change my color scheme. Right in the center, the mean, that's where it lives. And then just one standard deviation, two standard deviations, three standard deviations, 90, 80, 70. Right. And just like we did in the first group of questions, you can answer questions like, what percentage of people have IQs bigger than this number, less than that number, or between two numbers? So I could, for instance, find what percentage of IQs are greater than 123? What percentage of IQs, what's the average IQ of a football player? 80. Well, apart from the quarterbacks, they're probably quite high. And what's the probability that you get an IQ that's, put my little equals in, that is somewhere between 110 and say 95? So these are the kinds of questions you're going to be asked to do with a normal distribution, right? So I'm calling this IQ, but in general, they'll be called X, right? X bigger than 123, X less than or equal to 80, X between 95 and 110. Now, these questions can be answered using SOLVE. Now, that does mean that your next test will be in two places. I'll be putting some questions on WebAssign because you need to have access to SOLVE. And a fair chunk of your questions are going to be on that. And then the other questions will just be on a PDF. So you'll be doing a PDF kind of thing. That'll work. I'm sure it will. So let's figure out how to make it happen now. If you've got a fair degree of imagination, can you kind of tell what I'm going to do, even though I haven't done it yet? I'm back to that same picture, hopefully the same picture as we had the last time. You remember that one that we were using for the standardized Z-scores? And all I do is change the information. It's still 100, right? It's still normal. I go to the mean and I make it 100. And I go to the standard deviation and I make it 10. And do you see how the table has suddenly got some X's as well as Z's? It's kind of helpful. And now I want to answer, well, IQ is bigger than 123. Bigger than is that fella, right? And now that I've set it up, I can now go here and just type in 123. Hopefully. Oops. 123. And the answer I get is essentially, what's that? 0.011 if you round it off. So 1.1%. 1.1% of Americans have an IQ greater than 123. So if you have a nice high IQ, you're in quite an elite group of people, aren't you? You're almost in the top 1%. What about the football players? Okay, well, left tail. Now, see if you can't remember what the tails are. Can't you just click on the picture and then it kind of tells you what they do? Right. So less than. And I keep these because they're fixed now. And I just go down here and I change this to 80. And the answer is, as a decimal, to 3 decimal places, 0 to 3, which is about 2.3%. And hit both now, and I want 95 on one side. And over in the other side, I would like 110. And the answer I want is here. And that last answer is 0.0, oh, it's not, 0.4, that's better, 67. I hope you find this pretty straightforward, right? If you tell me the mean and standard deviation, I'll change my SALT table for this story. That's just visual to see where it's gone, but I can now answer a bigger than, a less than, or a between. You feel comfortable you could do that for not just IQs, but any combination I gave you. Right. So I'm going to try something here. It probably won't work, but I'm going to have a shot at it. Darn it, if I can hit it. Got it. Okay, got it. And I shall put this over here. Let's get some real data. And I want to compare two countries. And I'm interested in the percentage of people who are over 70. And I'm going to pick two countries and we're going to see if they are very similar or maybe quite different. And since I have no imagination, I'm going to pick United States of America as one of these. And the second one I'm going to pick is Japan. Melissa, that's your fault, right? Now, before I can do the analysis I want to do, don't I need to know what the mean and standard deviation of the ages of Americans are and what the mean and standard deviation for the ages of Japanese folk is? Now, what I'm predicting, fingers crossed, is will these two be the same? Do you think that the percentage of Japanese who are over 70, right? So the percentage of the entire population of Japan that's over 70. Do you think it's going to be pretty much similar to the Americans or more or less? What's your gut feeling? Because I know myself what it should be if I do this right.
I think Japan would be higher.
Yeah. The fancy word is demographics. The demographics of Japan and quite a lot of countries in Western Europe as well, are on the age side a lot older than America. In fact, I think one of the, do you know Brazil? That's the only one that comes to my head. Do you know Brazil? The demographics in Brazil are over 50% of Brazilians are less than 30. Half of Brazilians are 30 or younger, right? If you take some of the Western European countries like Germany and so on, they have very small family sizes and people tend to live quite a long time because of the medical system. So you're now about to see how things fail when you do something without planning ahead. I am about to try and collect data on America and Japan. And here goes. So I'm going to put in USA mean and standard deviation. Of ages. Now, hopefully that's going to get what I want. Here we are. The average life expectancy for this group is 89. The standard deviation would be 2. I better check that that's American. Oh, look, they're doing a kind of normal distribution. That's interesting. Uh-oh, it's Australia. Not interested in Australia. Yeah. I need help. Give me another search so I can find this. Let's do the mean age of Americans and see if that comes up. Mean age of Americans. There we go. With a bit of luck, it'll tell me standard deviation as well. I don't know what that is. Go away. The median age, well, it's not quite the mean, but it'll do. Oh, demographics, that's interesting. So it is 38.4. I need a standard deviation. Okay, I'll just do it as a search. Okay, standard deviation 7. I'll use that one. Better than nothing. Let's try Japan, maybe I'll get quicker. Okay, here's the median age. That might be interesting. Okay, 54.7. And for speed, I'm just going to pretend it's 7. It won't be that much different. Standard deviation doesn't vary as much as mean age. Right, so we got pretty close to accurate data. Right off the bat, isn't the average age of Japanese much older than the average age of an American? You agree? Now, I'm not too happy about the 7, but that's fine. Let's find, and that 7s can't be right. It isn't right. I can tell that 3 standard deviations is not going to be accurate for America. It isn't. That's just wrong. I don't know what standard deviation they were telling me, but it isn't the right one. Let's see if I can find another one. Okay. Okay, that's a good one. I think I got a good one here. I'm still looking for standard deviation. You know, when I close this class, I'll be able to find 10 examples of it. Right, the quickest one I've got is this table here, and it's telling me the growth rate, which isn't that interesting. But I should be able to do it from that to the mean and just divide it by 3. There, that makes more sense to me. Okay. That's a bit of a guesstimate, but it'll do. Right, now we should be able to figure this out. So for Japan, the percentage of the population who are over 70. So we're basically trying to find that answer. So I'll close this one off. I'll hit the salt button. Here we go. So thanks for hanging in there. I think next time I'll plan better. Right. Okay. For Japan, the average is 54.7. And the standard deviation, at least my guesstimate based on the demographics, was 15. I shouldn't be that far away. And we want to know bigger than 70 years old. Wow. About 15.4% of Japan is greater than or equal to 70. Do you know that's not unreasonable? That sounds about right. So I think I must have locked that out. Right, that's a pretty good number. And let's see what the USA looks like. So again, it's the same comparison. The only difference is that in the United States of America, the median age is 38.4. Mean, essentially. Keep the standard deviation the same. And now we're going to look at what percentage of those people are older than 70. And I'm not so happy with this answer, but I'll take it. It's about 1.8%. So what that is telling us is really that not all countries are the same. Now you might argue a little bit about, I don't think that's accurate. I'm pretty comfortable with that one, but this one I'm not so sure about. I'm sure about the result, that Japan has got problems. So you may think, well, what's the problem with Japan? If your population is age heavy, there are lots of things that people who are old do and don't do. Would you agree that most old people retire? In other words, they stop producing stuff. They stop being doctors, they stop being bus drivers or policemen or construction workers or anything else, right? Most of them will stop. So that means they're not producing anything towards the GDP of the country, right? Secondly, don't old people consume quite a lot of certain resources? They consume a lot of medical resources because you tend to be, you know, the older you get, the bits wore out, right? And you end up in the doctor more often, right? And so that's going to take up. So the net effect of those not producing and consuming more than a 12-year-old or a 22-year-old, medical things at least, is going to make a big strain on the country, which will probably mean that Japan in the next 20 years is going to suffer, I would predict, pretty bad financial strain on their economy, right? Because people expect a certain degree of, you know, living standards, and there's going to be fewer people producing for those who are receiving. America's not bad. I'm definitely, I disagree with that number. It's much bigger than that, but it ain't 15% either. America's much better off than some countries because the people who are, oh God, how do you phrase this without losing my job? The people who are in America right now in the usual way, their family sizes are quite small. So if America had no immigration at all, if nobody ever came to America, you would look very much like Japan in a couple of generations, right? You're only having 2 or 3 kids and you're living a long time. That's essentially what's happening to Japan, right? But because you've got other people coming in, immigration people coming in, they tend to have bigger families, and don't they tend to be young? So what that is doing is it's shifting the demographics of America in a way that there's still going to be quite a lot of young people. See, when I get old, I want young people to pay for my Social Security. Right? Do you know how Social Security was meant to work and how it really works are not the same thing? When I start getting my Social Security, the money I'm getting is essentially the money that David's putting in. And the reason why that's okay is David's working on the principle that when he gets to my age, Ashton or whoever it is that comes in the next generation, they're going to pay for his Social Security. So it's actually the generation before you that's paying for what you get. And don't you want to have lots of young people paying into Social Security so I can have it? Right. So none of you lot quit your jobs, because I need a good lifestyle when I retire. Okay, have a nice day, everybody. We'll call it a day.
Thank you. Bye.
Should
Bye.
we say hi?
Oh, say hi if you haven't said hi. Say hi quick. Everybody say hi.